Good afternoon. So who's on their cell phone tweeting, Facebooking, sending text messages? Yes. Yeah, we all love to multitask. So statistics actually show that 4 out of 5 Americans actually multitask while watching TV. And that can be from sharing commentary on the content they're watching, web browsing related to the content they're watching, or totally something different, like cooking dinner for the family, working out in the gym. That's 80% of the total population that is watching on average 4 hours of TV per day. And the total ad spend in 2013 is estimated to be $503 billion. Hi, my name is Usman Shakil, and I'll be talking about maximizing audience engagement in this media delivery. So what do our customers of today want? The customers really want to watch the content that matters to them from anywhere for free, whatever type of device they're using. They want to be able to easily access the content. It has to be nicely organized so it does not take me, hours just browsing through the content, what I want to really watch. And it has to be really high quality without any sort of irrelevant interruptions like annoying ads. So obviously some kind of personalized ads will be great, the things that I really care about or I'm interested in. And I would also like to multitask as well while watching TV for interactivity like second screen, social media, and all that kind of stuff. So really, an ultimate customer experience would entail an ultimate content discovery as well as the ultimate content delivery. And those are both things that we'll talk about today. So starting with content discovery, if we take a step back and we take the content choices evolution, from the number of channels that we used to have back in those good old days to today, we've got a lot of choices. And even more in the case of, the advent of digital media, that we have all these online mediums and channels now that we can watch and rewatch or replay that content. So yes, a lot of content choices. What about content discovery? Again, used to be those good old days of printed TV guides to the EPGs of your cable providers to second screen now, where you can actually look at the programming guide and all the different programs that are going to be in different channels, etc., while you're actually watching. So what that means is really a lot of options, a lot of choices out there. That's why we see a lot of our media companies today, spending a lot of resources, a lot of effort on really making this a personalized experience in terms of content discovery. So we see in the case of Samsung where they have unified search, you have all your favorites, you have all your different pieces of content that you want to watch, and you can search across all these different channels, to Netflix where they're spending a lot of resources to create things like personalized row displays and similarity algorithms, where it's really sort of almost like rocket science, to build these highly smart algorithms that look at what a person is or what an audience is really watching or wants to see and what their taste is based on their viewing habits and what to show or what content really means to them. And then the second piece is content delivery. So yeah, once I search for the content that I'm looking for, I'm interested in watching it, I need to have a great content viewing experience as well. So Conviva, a viewer experience report of 2013 shows that the average playtime per buffering percent is really directly related to the amount of buffering that you see. So basically, the better the quality the more viewing time that you're going to get out of your audience. And what this really entails is more time that the end user has on that screen or watching your content, more time with you, much more monetization opportunities. And of course, who likes these, right? It'd be great to see something that I really care about or I'm interested in. So really what's happening is that there is actually mountains of raw data from what a user is doing on the screen when they are trying to search for a particular piece of content, what different parts of a website or device or within that page they've gone and browsed, to actually what are they doing during while viewing that piece of content. So that leads us to two different distinctions between content discovery and content delivery. That within content discovery, you have the metadata, the session logs for that particular session that you can capture, and you can find out how did a end user reached to a conclusion or a piece of content that they really want to watch. To content delivery, that what their viewing habits were. Did they watch the entire piece of content? Did they skip in the middle? Did they close the session before that? Did they suffer any sort of like buffering or quality issues? Any sort of page click events? What happened at the CDN layer? To application logs if you have some sort of like a smart player that is streaming that piece of content. So in other words, a lot of data. So some numbers from Netflix, nearly 38 million customers that are, or unique customers that Netflix has in more than 50 countries and territories. That translates to hundreds of billion of events basically that are being generated in a very, very short period of time. So just imagine these 38 million customers, how many of those customers are actually watching content across 50 different countries, and what are the different events that are happening while that content is being streamed. At the same time, there is over 100 billion metadata events that are being triggered due to the activity that people have on, say, the Netflix website or the device where they're searching this. And the challenge is, how can we take this mountains of raw data that we just talked about to useful information as soon as possible? Kind of very similar to, I have a bunch of something meaningless, like the analogy I used here, like trash, and I want to sort it out on, how I want to use it for something useful. And that useful could be either historical data that I can use for batch analysis, or it could be live data as it comes in for some real-time analysis. So looking at the historical versus real-time analytics continuum here, I could either do real-time, which is 100% dynamic, meaning as the data is or as those events are being generated during a live session, I somehow capture those events and somehow process those events, and I'm able to get some useful information out of it. Or it could be batch, where it's I capture this information over a period of time, and then I could basically have some analytics processing happening behind the scenes, and I could get some meaningful information out of it, and then I could use this analysis for future purposes. So yes, obviously, I would love to have real-time information, but there are a lot of challenges with it. That is that it has to be computed on the fly. It's very flexible, but processing can take a lot of time, right, and a lot of power. We all know that at this scale. So really, it becomes a scale problem. That scale is very, very hard. In the case of batch, the reason I can't really use batch for everything is because it's predefined queries. It's rigid. I can't really run a query on the fly on a real time or set of events that are happening. So what I tried to do here was I really tried to divide it based on the use case. So on the real time side, that's really on the content delivery. that I want to do some sort of real-time capture, real-time analytics, and use that very useful information in my content delivery use case. Whereas I can use this historical metadata and do some processing in the back end and use this analysis for my content discovery purposes. So then, defining the challenge here, mountains of raw data coming from these events that are happening from very, very large number of user sessions out there. I need a way to, a scalable way to ingest and stream these mountains of raw data. Then I need a way to do real-time processing at scale. And then store it in a durable way and in a way that it is accessible to me for batch processing, and then I could create either dashboards, trigger events, and stuff like that, and take very useful actions on the fly or based on the user sessions to create really personalized experience for my end user. So really, that's going to be the track that we talk about how we do ultimate content discovery, and I leave it to our Shobana-Radhakrishnan from Netflix, and she will talk about how Netflix creates personalized content and the power of metadata. And ultimate content delivery, where I'll talk about the tool set for real-time big data processing and how it can be used in the context of media delivery. So I'll introduce Shobana from Netflix.
Thanks, Usman. How many of you have a Netflix service or have used it? Most of you, almost all. So you probably know that we are extremely passionate about making sure that the users have the most compelling choices in front of them when they're deciding what to watch on an evening. So why are we so obsessed with personalization? The two key metrics we care about as a streaming service are the median viewing hours, which is an indication of how much our subscribers like what they chose to see, and our net subscribers. So we want to grow, add more subscribers, but we also want to retain subscribers and keep them happy with our service. And through our A/B tests, as well as our different product rollouts, it's been clear to us that personalization consistently improves both of these metrics. And also, a significant percentage of what people watch comes from recommendations provided by us. So how do we do this? A critical piece of enabling this personalization is making sure that all the user-facing applications have access to all the data possible about our TV shows and movies. And this is referred to as video metadata. Simply put, video metadata is anything you have seen about movies. It could be genre, cast, rating, just contract information. Do we have an exclusive contract? Are we allowed to show it in all countries? How long does this run for? What languages are we allowed to show? Even information like that. And all the information about what devices we have encoding for, what bit rates we can support for each of the shows, how many episodes do we have trailers for. So all this is referred to as streaming information, any information about assets or the actual streams. And also the deployment information itself, which origin service is this content hosted, which one is closest to the locale that's interested most in this movie. Even those are referred to as metadata. And a number of pieces are actually localized. For example, the subtitles, dubbing, trailers, stills, even the titles on the billboards, all of those are localized and therefore tailored again to the audience. This is also referred to as metadata. So there is a wealth of data about the movies that we can use to make sure we provide the best possible viewing experience. What is it used for? Providing using user-specific choices like language or even the viewing behavior of the specific culture of their locale, their taste preferences. All our recommendation algorithms, you probably know about similarity and a number of like top 10 recommendations from your Netflix interface. Pretty much every row that's presented to the user is running some algorithm which heavily leverages our metadata. Device rendering and playback, as we talked about earlier, CDN deployments, all the assets related to the movie or the show. Original programming has been a big part of our focus recently. How many of you have seen House of Cards or know about it? How many of you know that we won Emmys for House of Cards? Great. So you can see why we focus on this part of our business as well. So international expansion as well as original programming have been our focus and are going to continue to be a big part of our focus. So basically everything, anything that's related to providing a rich experience for the user is going to heavily use metadata. So as Usman was talking about earlier, we have a number of data sources. The processing that it takes to enter this data into our systems, whether it's encoding or just review of the content, automatic generation, re-encoding of the content, all these generate metadata. There are distributed workflows done by several teams and tools that feed metadata into our system. Now, our job in our video metadata infrastructure is to make sure that we extract the relevant data that each application cares about and provide it in the most efficient way possible for these applications. Because as you know, availability is a big deal for us. We guarantee 4 nines for our streaming service, which heavily uses metadata. So the playback uses metadata. So we need to be really efficient about this. So at high level, our solution was to have a publishing engine which understands the different sources of truth and is able to operate on that piece of data, make it very efficient, generate slices of the data that our applications care about, and write it to S3. And then on the client side, we provide an object cache. So all the applications in Netflix, all they have to do is pull this jar in, and they're able to access the objects they care about. They don't even know where it comes from, how it gets refreshed into memory. All they know is they get a very efficient access, and they have guaranteed in-memory access to all of this data. And their availability is not at risk with the solution. That's really all they should care about. So our architecture looks like this, as I said earlier. The snapshot files are also referred to as cold start files because we can, in seconds, pin systems to an old, known, good snapshot of the data if we detect that there's anything bad about the data. And that's why it's also referred to as cold start. So with every cycle, the publishing engine generates about 10 facets per country and writes them to S3 in this architecture. And most of our application, so when we started off, there were a couple of thousand instances across our applications, all of them using EC2. And they used to access this data on S3 during cache refresh. So in terms of the data flow, just a simple sequencing diagram to demonstrate that. So metadata gets entered through these variety of sources. There are hourly data snapshots. Again, the frequency can be adjusted. We also now support event-based generation of data on this side. The publishing engine periodically checks, do you have any updates for me? It looks at the deltas. It generates and writes also the artifacts to S3. And then the cache, through its periodic refresh, is going to get this data from S3. What this means also is, since we extensively use auto-scaling from AWS, we need to make sure that our cache warm-up is very quick, very efficient, because our instances are being dynamically started all the time for all our applications. So this cache can't slow down the startup time. So that is a big deal for us. And the periodic refreshes need to be even more efficient and non-invasive. So at this point, all the applications have to do is make Java API calls, and they get access to the data and serve the users. So our initial landscape was we established ourselves in US and Canada first. And as I said earlier, a couple of thousand EC2 instances were accessing us. So this architecture worked really well. 100% of the data is always in memory. So you're guaranteed to have the in-memory latency for all of the data. So the target application looks something like this in terms of file size, number of instances. You can do the math in terms of the S3 reads per cycle. And our availability goals are pretty stringent. So our solution was to provide 100% of the access in memory. And then with an ever-growing business like Netflix, nothing stays static, as we all know. So a few things happened that made us enhance this further. So we went to Latin America, which added a bunch of countries to the mix, and we have expanded since. We have most recently launched in Netherlands in the past September. And we also had more applications in Netflix that started using this to personalize their algorithms even more. So the number of instances that needed to access this data also grew significantly. So we had a problem to solve or scale. So from the previous slide, these are the corrections. So with the same architecture as before, where we wrote 10 facets per country per cycle, now we're writing every cycle, we have 500 writes, and a large number of instances trying to access all these files and refresh themselves. But we still had the same availability guarantees to work with, the same make sure that the cache can warm up quickly and applications can start up quickly for auto scaling. So as you might expect, with that, with the initial implementation, as the data grew and the number of fetches grew, the file writes we saw were slower because just a lot more data being written. Longer publish time because the publishing engine is trying to write a lot more things with each cycle, and also it's processing, deduping, filtering through a lot more data. And since there was a lot of client-side processing to read all these facets, dedupe, and then figure out this is the part I need, there was overhead involved in the startup and refresh as well. So there was a higher cost on the client side. So a couple of key things we did is, one, we re-architected the publishing engine to be region-based instead of just a simple one per country. Or it can even be configured to be one global server, which would crunch all the data, dedupe, and do a lot of processing in the pre-write phase, which is before even writing the facets to S3. And we also came up with this design of blob images, which are not just slices of data generated per country, but it supported a combination of both horizontal and vertical slicing. For example, you could say, I want only data for LATAM, or I want only data for this region, because you may be a regionally distributed service. Or you could say, don't give me streams data, because I don't care about that, because maybe I'm an algorithm that doesn't use that data. So we allowed more intelligent slicing of the data, so the number of images we produced also could go down for satisfying all the needs. So from 500, we were able to bring it to basically writing 10 blobs per cycle to S3. And as I said earlier, a lot of the deduping, a lot of the processing was moved to the pre-write, which means the client-side processing has become much simpler now. And so the cache warm-up, as in startup time, and refresh times went down significantly. Another thing we did, which was not necessarily a change later, that's the way we did it from the initial, is the cold start files are written in zipped format. So the smaller the files you write to S3, the fewer the files you write, the more efficient your application is going to be. We also used the trick of, from the publishing engine down to the client. Since after the initial startup, applications are more interested in knowing what has changed since I last read. They're not interested in the entire snapshot. The snapshot is really for fallback or for recovery. So we prioritized to write all the deltas first so that we could get that quickly in the hands of the application, and the snapshot could come later. So we used even small tricks like this to make sure our cross-region publishing as well as our delta and snapshot publishing was very efficient. So we did observe a significant reduction in the average memory footprint of the cache in the application itself, because a lot of the deduping and optimization is happening on the server side. We saw, as a result of this, significant reduction in the application startup times, and also shorter publish times because we were writing fewer files per cycle. A few things we learned in the process. And in-memory cache, we leverage Netflix graph, which is actually open sourced. If you're interested, there is a write-up on this on our tech blog. This is very effective for high availability because in our design, we have basically eliminated network latency for real-time requests with this solution. Startup time is critical when you're employing AWS auto-scaling, so that's always been a key metric for us to optimize. In fact, now we are on a continuous deployment cycle where we actually measure the startup time for each of our blob image combinations for every check-in. So you can detect regression pretty quickly and adjust it, so every release goes out with us knowing exactly how the footprint and the behavioral characteristics are going to be when our cache runs within an application. Definitely use the best practices documented by Amazon. A couple of other things. This is an extremely distributed system where there's a lot of data processing going on at every stage. So we employed circuit breakers, both, as you saw, it's a mix of both offline processing and real-time access. So we had checks and balances to make sure that the data didn't deviate much from what we would expect. So when we saw a trend of data where, for example, say the number of titles going live was much more than expected or much less than expected, it would alert automatically and trigger a whole on-call process to fix well before a customer could notice it. And as I said earlier, we could pin back to a known good snapshot in seconds. So as long as there was very good monitoring across the board, and there was a clear way of alerting crisply, we were able to roll all these fundamental changes out without any impact to the customers. And also, because we have a very lightweight coordination culture, even though more than 25 teams use our systems, and we work with almost 10 teams on the source side, we were able to roll these changes out in a matter of weeks, because most of the teams, in fact, all the teams have automation and continuous deployment as part of their life cycle. So it's actually very lightweight to make even pretty fundamental changes, such as this one. So with that, just wanted to share a few things we are thinking about for even further scale. If you think of, say, 5 years from now or 10 years from now, the growth for Netflix as well as what we will support, a lot more data is going to go through the system. We're going to be serving a much higher number of requests from users. So a few things we are already starting to think about is providing a number of dimensions to dynamically control the cache's behavior, because each of our applications has a different access pattern. So it's not possible for one team to think about everything and provide one solution that fits all. So we're going to do a lot more of that. We're experimenting with dynamic code inclusion, where different people can contribute and shape how the optimization works. And also, we're looking to parallelize our publishing engine itself, because as more data goes through it and more complex relationships between the data develop, it's going to become more complex and probably more heavyweight to do the publishing side as well. So these are 3 angles along which we're already thinking about for further expansion. Great. With that, let me turn it back to Usman.
All right. So with these great techniques, metadata, so assuming with the great customer or content discovery, the customer is now already set to what they want to watch. Now time comes for content delivery. We want to give them the ultimate content delivery. And what I want to really talk about here is take this opportunity to talk about the tool set that's available out there on AWS that will allow you to build a real-time big data processing application that you can then use for real-time decision making to get to this ultimate content delivery. So back to the challenge again. We have mountains of raw data coming in, have to somehow ingest, stream into real-time processing, and then use it for dashboards or personalized user experience. So first comes ingest and stream. So here, going back to our real-time versus batch continuum, I have on the right-hand side, starting from batch use cases, Amazon S3. You're probably familiar with Amazon S3. Highly scalable, simple storage service allows you to store static objects. So basically, one thing would be as those events are being captured, as those events are being happening while the content is being delivered, you keep on putting those things into S3, start dumping into S3. One beautiful thing about S3 is that it scales automatically for your use. So, you can just start this fire hose of these logs going into S3 and start dumping them in there. Next down the list is SQS and DynamoDB. If you notice, I put an arrow in there because these are dynamic, because SQS scales based on the traffic, or based on how you're putting or the messages into the queue, and DynamoDB you can really provision it for the throughput that you're looking for, so you can really scale these things as needed. But S3, SQS, DynamoDB really work for the batch use case where you have a lot of data that you are somehow capturing into these storage backend systems, and then you are using some sort of like a batch processing like Hadoop, et cetera, to run some sort of analytics on it and then use it for your batch processing needs. How about real time? So I'd like to talk about Apache Kafka. it's an open source project, basically gives you the capability to build scalable messaging clusters. So basically you can define different partitions and then from there on push these event logs getting into these partitions and scale based on the demands of your application or based on the throughput that you're looking for. And the new thing, Amazon Kinesis, that we just introduced this morning, which is a highly scalable, highly available, and durable messaging service. So basically it gives you the capability to, again, scale based on the demands. How much, events, how many events that you're looking for that are going to be pushed into this messaging queue. So I'd like to talk a bit about Amazon Kinesis. As you know, it's a new service that scales elastically for near real-time processing of streaming data. So the service stores large amounts of data in a durable, consistent storage, which you can scale. And it is good for real-time processing that, as I mentioned, that you can scale. So the way that works is that you have a bunch of streams that could be any data sources. In our example, back to the media delivery case, we have a stream that is being played, and all those events are being captured. So those are from everywhere. They are talking via the Amazon web into the Amazon Kinesis backend engine, which is really a storage system. So what it is it allows the developers to define the number of shards that they want to have. So based on the shards, it will scale, and that will define the eventual throughput that you can have from Kinesis. And so you use the Kinesis put API to put these event logs into these shards, and then use the get from the Kinesis API to actually get those event logs, run it into your application for processing, which you can use, again, Amazon Kinesis enabled application or API to do certain things like filtering, find uniques, doing aggregations and stuff like that. And then once the processing is done, actually delete it from Kinesis. And then you can also store it into a durable storage system like S3, DynamoDB, or Redshift for further analysis or further usage as well. So quick intro to Kinesis. So at its core, Kinesis is a storage system Kinesis storage system is actually a high performance and strongly consistent replicated log system. So it also employs chain replication, which means that it maintains high throughput and availability without sacrificing the strong consistency guarantees. So basically, as you can see here, it's a managed service, as I mentioned, transports data streams. It enables the users to launch multiple shards, or you can specify how many multiples of 1 megabyte per second shards you want to have. Each shard is capable of doing 1 megabyte per second. So basically, you can scale it based on the throughput that you're looking for. Each one of these shards is stored for 24 hours, and it's highly durable, and it is achieved by a three-way replication. So behind the scenes, we are replicating it in multiple availability zones. And each data record that you put into the Kinesis shard is actually assigned a sequence number. So based on that sequence number, then you will be able to get it. So in the picture, then there are the producers, basically that generate these streams of data. And they use the Kinesis put API to put this event logs or data into these shards. And they use a partition key, which is supplied by the developer or the producer, and places the record into a specific shard based on this partition key. So once all this data is in there, so that's the ingest piece that, all this millions of events or, however many hundreds of millions of events that are happening at any given time, you're storing those, throwing those into these shards. And then there is the consumer layer or the worker layer, which is basically a processing layer running on EC2 that, again, a developer owns and controls and uses the sequence number that we talked about earlier to get these records from any one of these shards as possible. So the idea is that you can really scale up to gigabytes of data per second, literally, or hundreds of millions of records per second. And then you could do real-time processing in the matter of few seconds. So that was the ingest piece. Now let's talk about processing. So once the data is in there in our durable, highly performant storage system, Kinesis, these are the different processing tools that are available out there that you can run on Amazon EC2 and do real-time processing of this event data. So again, on that, on the right-hand side, the batch side of things, you could run Hadoop using Amazon EMR. You can scale Amazon EMR, based on the number of worker nodes that you want to have, and based on the urgency of this analysis that you want to do, you can scale it up or down. And it's a managed service within Amazon Services Stack. Once the data is analyzed using the MapReduce or some other processing technique, you can then push it into Redshift, and then it becomes readily available for you to query it. You can also use Redshift's processing power, so basically if it's simple aggregations or simple queries within Redshift, Redshift tends to perform very well. But again, the idea there is that you can scale both EMR and Redshift based on how quickly you want to analyze this data. But again, both of these go into the batch specific use case where you are working on it on a historical set of data, storing it, and then using the analysis for personalization type of use cases. Let's talk about Storm and Spark. So a quick introduction to Storm. A Storm is really similar to a Hadoop cluster. Basically, Storm is open source, and there is a concept of topology versus a job. So when you're running a Hadoop job, basically you have a data set for a particular timeline that you're running a processing on. Whereas in the case of Storm, it's really the incoming stream of data that we captured using, say, Kinesis or Kafka or some other technology like that. And it is a continuous job that you're running or continuous analysis that you're running unless you really go and kill the topology. Very simple to run it. And what it does is it really the streams like unbounded sequence of tuples, and I'll talk about it. These tuples, there is a concept of a stream, a spout, and a bolt. And what I did was I actually took the example from the Storm documentation and kind of modified it into our particular use case. So in this particular scenario, I'm really interested in getting the count of ads that were clicked on and watched in a particular stream. So just imagine, if I am if I have a bunch of streams in a channel or in a media delivery workflow, and each one of these streams have an ad playing, that could be a personalized ad or whatever, I want to make sure, I want to get a capture of how many ads are being played. So the first line, actually, I go create a topology. As I mentioned, topology is sort of analogous to a job, but it runs forever. And then I use that topology to add a bolt. So bolt is a processing piece within Storm. And what this bolt is going to do is it's going to get the stream. So it gets all the streams, and it is going to transform the ID, transform a stream of IDs and ads to IDs and streams. The next piece is to filter out the viewers or get the viewers of a particular ad within a stream. So in the first step, we got which ad is specific to a stream. And then the second one, we got the viewers of a particular ad. Okay. The third one here basically does a unique count of the viewers of that ad and a full view of a particular ad. And then finally it computes the aggregate of the viewers. So behind the scenes, it is, it has all these different methods like counting doing the aggregations or doing the partial uniquers, et cetera. Those are defined. But the idea is it's very, very simple to implement, simple to code. So putting it all together in terms of using Kinesis along with Storm, here I have a bunch of streams of these events that could be, as I mentioned, multiple different streams playing and producing these event logs that are shoved into the Kinesis shards or Kinesis storage. And then I use the Kinesis API to create these spouts that are consumed by Storm bolts that are actually processing nodes that could be running on EC2 and scalable to do real-time analytics of the data. So that was real-time analytics of the data as it comes in. Basically, it's running all the time, the topology is running all the time. Now, let's talk about Spark for a bit. Spark is also open source, started from the Berkeley Labs. And really what Spark is it's sort of in-memory batch processing. So the big difference between Spark and Hadoop would be where Hadoop runs on a disk-based processing nodes. Spark could be in memory. So the real benefit there is that you can use the data set that is in memory for iterative type of processing needs that you have. So again, taking an example from Spark and kind of putting it into our sort of example. So in this case, I'm interested in counting the buffering events from a streaming log. So again, I could use Kinesis or something similar to capture the event logs from a stream. In this case, I have the stream that is stored in some location as a text file, and I simply filter these logs for the line that starts with a buffer, and then I persist that in memory, and then I count those. So behind the scenes, what's happening is when I run this Spark job, at first action that is involving buffer, it runs the Spark process, and the driver will take the data set and put it into the processing node. So each one of in this case, there are 3 different processing nodes, and each one of those has the input data. It is read in memory and then processed. And then it is basically persisted in memory for further processing. So that's the key piece that I want to bring to front here, is that it's the in-memory processing of, say, a smaller micro set of the data set that is being processed in this case. So in our logistic regression performance example, basically that was a test run between Hadoop and Spark. As you can see, in the very first iteration, it actually took 174 seconds for Spark to run the logistic regression, whereas for Hadoop, it took 127 seconds. So the very first iteration, it's actually faster to run in Hadoop. But for ongoing cases, since now the data set is persisted in memory, and you can bring more data set as it grows and basically rerun or do additional iterations, it is much faster in Spark just by virtue of the fact that it is persisted in memory. So again, a more relevant example in the case of Conviva GeoReport, aggregations are many keys. Basically, if you look at Hive versus Spark, to run the particular report, it took 20 hours on Hive, where Hive is SQL on top of SQL interface on top of Hadoop, and in the case of Spark, it took half an hour. So that 40 times gain actually comes from not having to read this data set over again, in order to do the iteration. Rather, use the data set that is already in memory and persisted in memory. So different tool set in the case of processing from, say, Storm for continuous processing of incoming streams to small micro level batches in the case of Spark, and you can scale Spark for much smaller micro level batches to sort of give you this real-time processing needs as you're looking for. So from processing, moving on to the backend storage. So I have ingest. I have a way to do scalable ingest, basically as the real-time events are being generated. I have a way to process my events from batch all the way to real-time, from as I talked about, from EMR, Hadoop to Storm and Spark. And so once I have this data set that's being processed, that's already processed now, I can store it into S3, where I can access it at given time. But from S3 perspective, it's going to be an object which is sitting there, and I can access it. There is obviously depending on how I access it, there is it's good for the batch use cases. Then there is RDS, the relational database, Amazon RDS service, where it could have a relational schema and could be stored inside of a database. DynamoDB, where I could provision the throughput, and based on my needs, I could simply go and do a NoSQL type of a get from DynamoDB. HDFS on Amazon EMR, again, I can scale it based on the number of nodes, the size of nodes that I have, how much performant, how much size that I want on HDFS, and store it. And then finally, Redshift. Redshift I can use for sort of data warehousing type of needs, where I have done some pre-processing on the data set on a real-time basis, and then put it into Redshift that then I can use for historical processing, historical data processing as well, using Redshift's aggregation processing performance gains there as well. So finally, some batch processing techniques. We could obviously use EMR with Hive on EMR. It's good for custom user-defined functions, and if there are needs for, say, like data warehousing type of needs. And Redshift for more traditional type of data warehousing needs, where I could run the ETL process either as real-time or in the batch, put stuff in Redshift, and then consume it later. So putting it all together, the challenge was mountains of raw data. How do I ingest it? How do I process it real-time? Store it in a more scalable way, do some batch processing, and be able to run, make decisions on the fly and take actions. So from a tool set perspective, from ingest and streaming side of things, we talked about from S3, simple queuing service, Amazon DynamoDB, Kafka, and Amazon Kinesis. On real-time processing side of things, we talked about Amazon EMR, Redshift. We talked about Storm and Spark. For storage, data warehousing, Amazon S3, Amazon RDS service, DynamoDB, and then Redshift. And then finally, I could use EMR for backend processing. And all that gets me to useful information that I can use to make decisions like dynamic personalized ads. Now that I know that how somebody is consuming those ads, or where are they watching from, what are they watching, what are their sort of viewing habits on the fly, I can take actions in terms of how or what type of ads or personalized ads that I want to display in that stream. Dynamic CDN switching, that's a big use case. We see some companies already doing that using Kafka, Storm type of technologies, where basically based on the user experience or the quality of the stream, I could do CDN switching on the fly, switch them from one CDN to another based on how one CDN is performing in a particular geographic location. There are other things like interactive streaming experiences as well, where while somebody is watching a stream, they are able to say do some sort of like social interaction, like via social media, or interact directly, have analytics on the content itself, and then finally stream quality in terms of again better stream quality, better viewing experience for the end consumer. So finally, what we talked about in this, kind of recapping this whole thing, what we talked about or tried to convey in this is the tool set around, the time frame when somebody sits at that, couch, picks up the remote and wants to watch something, to they pick the content that they start watching all the way to an ultimate entertainment experience where, they love consuming that material. So for more information for Amazon Kinesis, the web page is up and running. take a look at it, try it out. It's very, very cheap. I'm happy to say that. Other resources, Apache Kafka website is there, Storm and Apache Spark. Good technologies to take a look at it for real-time processing. Thank you very much for joining us today, and I really hope that you find this useful. Myself and Shobana will make ourselves available here to take any questions and answers questions that you guys have. Thank you very much.